Alright, so now we'll talk about geometric series. An infinite sum of the form a1 plus a1r. So you see that those are the terms of a geometric sequence. These are the terms of a geometric sequence being added up. That's actually the nth term of a geometric sequence, but we go beyond that and we go all the way out to infinity. So we add up all the infinitely many terms of this sequence. We're adding them all up, infinitely many. And how could this infinite sum ever equal a finite number? Well, it turns out that if r, the common ratio, if the common ratio is between negative 1 and 1, so basically, if we know that on the number line you have negative 1 and positive 1, if you know that your common ratio falls on this open interval between here, so it can't be 1 or negative 1, obviously, but if it's a number between 1 and negative 1, if your common ratio is somewhere on this interval, then that infinite sum is actually going to give you a finite number. That infinite sum will actually give you a finite number. And the number that it's going to give you is this number right here. So it turns out that this sum from I equals 1 to infinity of infinitely many terms would just be whatever this gives you. The first term divided by 1 minus the common ratio. Pretty straightforward. Here's an example. Well, let me see. So we would need to know the first term, and that's pretty straightforward there. 12, because the formula says the first term over 1 minus the common ratio. Next thing I need to know is the common ratio. Well, it's the ratio of consecutive terms. So those consecutive terms, even those consecutive terms, all have the same ratio. That ratio is equal to negative 1 half. So negative 1 half is the common ratio. The formula says that this infinite sum, the sum of this geometric sequence, is going to be equal to a1, which is 12, over 1 minus r, which is 1 minus negative 1 half. So we can find this sum by finding out 12 over 1 minus negative 1 half, which is equal to 12 over 3 halves, and 12 over 1 you multiply by 2 over 3 and we get 8. So this sum equals just 8. This adds all up to 8. So 8 would be my final answer. All these numbers, infinitely many, added up, just add up to 8. Crazy. Here's another application. This is a repeating decimal. And I want to write this repeating decimal as a fraction in its lowest terms. So let's go ahead and do that. So let me see. Let's write out this repeating decimal. Let's expand it a little bit. So this would be 0.0252525, and of course it would continue like that forever. Now let's write these as fractions. So first off, let's actually take a look at the first three terms here and write them as fractions. So let's take a look at just these first, oops, I keep doing the same thing here. Let's take a look at just these first three terms and write them as a fraction. So the sum of those first three terms, let's see, we got 25 over, that's tenths, hundredth, thousandths. That's 25 over 1,000. Plus, the next one is going to be 25 over, well, that's 10,000, 100,000. So 100,000. And then, of course, you have, this is the millionth place, this is the 10 millionth place. So that's 25 over 10 million. Okay, and then, of course, it continues on like that. There's infinitely many more 25s to add up. So this is an infinite series. Let's see if it's geometric. Okay, well, that the sum of all those fractions. Let me clean it up a little bit first. I'm going to clean it up by factoring out the first term, 25 over 1000, to see what I get. If I factor out a 25 over 1000, that first thing just becomes 1, while the second thing becomes 1 over, because you're dividing 25 over 100,000 by 25 over 1000, 3 of those zeros would cancel and you just get 1 over 100. The next one would be 1 over, well, that's 10 million divided by 1000, right? 10 million, when you divide by 1000, 3 of the zeros cancel and you get 10,000. And then, of course, you continue on like this forever. I'm going to rewrite that just one more time. This is over 1000. As 1 plus 1 over 100, and it turns out that 10,000 is actually 100 squared. So there's actually a pattern there. There's actually a pattern. So this is geometric in nature. The nth term would be just 1 over 100. And if you notice, if this is the first term, that's just 0 power. This is the second term, that's 100 to the first power. The third term is 100 to the second power. So it would be 100 to the power of n minus 1. But then, of course, this continues on. You don't stop. You continue on with that. But this is geometric, is my point. And the common ratio is 1 over 100. The common ratio is 1 over 100. So I can write this as the sum from I equals 1 to infinity of A1, which is 1, times R, which is 1 over 100. If you take a look, that's the common ratio between all these terms, raised to the power of I minus 1, which is a infinite geometric series. That's a geometric series. So I can find the sum of that series, that infinitely many terms. I can find it by doing the formula that we just learned. This is multiplied by this thing. So it's A1, which is 1, over 1 minus R, which is 1 over 100. So we get that this is 25 over 100 multiplied by the reciprocal of 1 minus 1 over 100 is 99 over 100. So this is 25 over 100 multiplied by 100 over 99. But we still have this to consider, right? So we still have, oops, and where did I get 100? I dropped a 0 somewhere back there. That's actually 1,000. It's actually 1,000. It's actually 1,000. My fault. So I just dropped a 0 arbitrarily. There was a 0 there from the very beginning. It was 1,000, and I just dropped it. All right. So now everything is copacetic. So we can cancel out 2 of these zeros. And this turns out to be just 25 over 990. 25 over 990. But when we have to simplify that fraction, and the number that goes into both of those is 5, so simplifying, we get that this is just equal to 5 over 198. 5 over 198. And if you do that division on your calculator, you'll see that 5 over 198 is actually 0.025 repeating. And that's one of the applications of the infinite geometric series.